So yeah, okay. Okay, so yeah, welcome everyone. It's a pleasure to have Professor Aarti Gupta with us. Aarti is a professor at Princeton University. And before that, she was working in NEC for many years, leading the verification team. And before that, she did a PhD at CMU and I believe her undergrad at IT Delhi. And so I think Aarti is quite unique in terms of the breadth of areas that she's worked in. I think that's truly impressive, from hardware verification to model checking to concurrency, distributed systems, program analysis, formal methods theory, data races, and including decision procedures and testing and simulation. So I think almost anything that you can think of, Aarti has a finger in that pie and contributed interesting and lasting results to the area. So Aarti, welcome to this seminar series. And today Aarti will be telling us about her work in verifying network control planes. So over to you, Aarti.
Thank you so much. Thanks for the kind introduction and for inviting me. Yeah, this is, I wanted to share the story of what I've been doing since I moved from NEC to Princeton. And as you pointed out, Deepak, I've spent a big part of my career in hardware verification, software verification. So it was nice to do something slightly different for a change when I arrived at Princeton. And this has been really a true collaboration with Professor Dave Walker, who's been also working in the area of programming languages and networks for quite some time, along with his students, Ryan Beckett and Ratul Mahajan, who's at University of Washington, and now our students, Divya Raghunathan and Tim Tyne. So networks, the one thing that I learned or relearned about networks when I started working in this area was that you can think of them as being separated into a control plane, and that's where they run routing protocols, and those are determined by the configurations that are set on the different routers. And there are several control plane protocols, legacy, that are used even now, RIP, OSPF, BGP, and so on. I won't even be talking actually about the new trend, which is software-defined networks. For the talk today, I'll be focusing still on distributed routing protocols. And once the control plane makes the decision about how to forward packets, then the data plane kicks in. It really has these forwarding tables, if you will, which tell you if a packet is headed for a certain destination from a certain source, then forward it on this port and so on. So these are essentially data forwarding packet forwarding tables, and that's the data plane that emerges from the decision process that happens in the control plane, where the routers exchange messages with each other in order to decide which route to pick. And both of these together result in the runtime behavior that we see, where packets are sent to a router, which is then consults its forwarding table and sends it off to a different router on a certain port and so on. So it's useful to keep in mind this distinction between the control plane and the data plane. In the control plane, it's the routers that are exchanging messages with each other, whereas in the data plane, it's the packets that are getting forwarded between routers. So as I said in the title, the focus for me has been verification of the network control plane, where the primary goal is to get traffic from point A to point B. But of course, this is easier said than done because there are security considerations, there may be firewalls and so on. There's traffic engineering considerations where you want to minimize congestion and utilize the bandwidth available and so on. You have to, of course, worry in networks about fault tolerance because certain nodes may go down, certain links may go down. And so you should have backups for various reaching certain destinations and so on. And all of this is, affected also by cost considerations. And so the way that these networks are programmed in the control plane are through what are called configurations at each router. You can think of the configuration as being a distributed program. Unfortunately, the language that they use is very, very vendor specific. So Cisco will have its own language, Juniper will have its own, and so on. It's also really low level. You can think of it as almost assembly language level. And so there's thousands of lines which people are afraid to touch just because nobody knows what might happen if you change any of these lines. And so misconfiguration, which means bugs in the configuration, is a huge, big problem. And there's just every day, every week, there's just some outage or another, which causes a lot of pain, both to customers as well as service providers and so on. So there has been a lot of interest, and this motivated many formal verification efforts starting about a decade or so ago. And the first batch of these was targeted for what are called data plane verification. They check a snapshot of the network. So basically, data plane is the part which has those forwarding tables. So data plane verifiers simply check the given forwarding rules at the routers to check various properties. And as you can imagine, they have used all kinds of techniques based on model checking, symbolic simulation, SAT, SMT, BDD-based techniques. And there's been so much progress that they are now routinely applied in large data center, some with tens of thousands of routers. And you might have heard of some of these very successful data plane verifiers. I've listed a few of these, which were really trailblazers in terms of applying formal verification techniques to find correctness bugs in the data plane of networks. The control plane has been a little bit less studied, also because it's more challenging, because here the control plane verification checks if the router configurations that determine the data forwarding rules are correct. So really the job is to verify all possible data planes that result from the configurations, not just a single given one like the data plane verifiers do, but all possible data planes. And again, these techniques have been based on model checking, graph-based techniques, SAT, SMT, BDD, and so on. And so far, they've been demonstrated on about 2,000 to 3,000 routers maximum. I mean, many of these techniques scale only up to about hundreds of them and so on. But let me point out here also, there's two main kinds of efforts. One are what are called control plane simulators. And you can think of these as testing. You are given a testing environment, you're given an environment in which the network is operating, which means these are the external announcements at the edge of the network. And Badfish is a very, very well-known control plane simulator. In fact, one of the very nice things Badfish did was it extracted logic-based behavior from vendor-specific languages. So you can think of it as a very nice front end that understands the vendor-specific configuration languages and gives you, as an intermediate representation, a logic-based constraints or rules for how the network control plane behaves. In fact, for many of our tools, we've used Badfish as our front end. Control plane verifiers, on the other hand, are not just simulating a given routing announcement, but they try and verify all possible announcements to various degrees. And here, I will just point out that some of these are based on symbolic execution. Some are just explicit graph-based techniques where they've applied max flow-like techniques to do failure analysis. Some of these are semi-symbolic, so they have a mix of explicit graph-based techniques and model checking combined with some kind of SMT or SAT-based methods. Our work that I'm going to describe today is very much focused on fully symbolic approaches. What can I say? I just love SAT and SMT solvers and BDDs too. So that's what we focused on, basically providing a fully symbolic approach. Let me also say that I'd be happy to take questions along the way. I know that I have always, as always, way too many slides, but I'd rather keep it interactive instead of losing people along the way. So you may ask what kind of network properties are being checked. A very common one is that of reachability, where network administrators want to make sure that a certain destination is reachable from a certain node, for example, in the data center, and they may then want to check it for all source destination pairs. Another property is called a no transit property. And here it's when there are some external nodes outside of a data center, then you want to maintain certain business relationships. So you want to make sure that nobody's using your data center network simply to transit into reaching another node that is outside of your network. So that's called a no transit property. Another common property is checking router or subnet equivalence, and that's because they may want to change a certain configuration or a certain topology, and they want to make sure that that would not inadvertently introduce any bugs. No routing loops is, of course, a very important consideration, and that's something that is either guaranteed by design of some of the protocols, or it can be something that can be checked. Black holes are places where inadvertently packets get dropped without anybody becoming the wiser. So no black hole is another important property that network administrators often want to check. Any questions so far?
So,
Okay.
Aarti, one quick question. So maybe I missed that, but what does the control plane do? Does it, take packets from the routers and,
I'm going to tell you in a second.
Okay, sure.
So if you just give me like 30 seconds, I'll get it.
Sure.
All right, so let me talk about our first effort that we made then, which was modeling the network control plane. And that's
Aarti, I have a question.
Sure.
So these properties, if you go back to the different previous slides, so the properties that so don't they cut across layers? Like it was, do they sometimes you distinguish between the control plane and the data plane? So right. Some of these properties, don't they require, might they not require both?
Yes, they would. You're absolutely right. So what I'm talking about is if the control plane itself doesn't have reachability, you can't have reachability in the data plane at all.
Oh, I see. So these properties.
So the data plane is, will further add things like ACL rules and so on. Mm-hmm. So you need to have control plane reachability first, and then the data plane may further add filters and so on. Hmm. So often, at least for protocol and configurations, you want to know that the control plane, there is reachability. Hmm. So that's what I'm talking about here. And some of the tools I'll talk about can actually combine control plane with data plane, like the next tool that I'm going to talk about, Minesweeper. Our work does that.
Okay.
So a related question. So I thought you said that you will check all possible data planes that arise from one thing. So do you check reachability for all possible data planes or for the control plane?
We will check reachability for all possible data planes that would emerge from the control plane configurations.
Okay, so all these properties you check on all possible data planes, but not on the control plane itself.
No, yes, that's right.
Okay.
Okay, so let's move on. And this is the first work that we did, which was really addressing the question Deepak had asked: how do you model the network control planes? And I'm going to talk specifically about our work called Minesweeper, which was published in SIGCOMM 2017. So let me first describe what's a generic routing protocol. And there was very nice work done by Griffin and Sobrino, where they basically studied many different protocols in existence and came up with a generic routing protocol, which can be understood like follows. The origin creates an initial announcement stating it has a path to destination D. So here is an idealized RIP. It's a very simple routing protocol. Let's say a particular node is the destination D. So it's going to say, I have a route with distance 0 to myself. So that's an initial announcement that gets created. I'm sorry, I have to. Oops. Okay, sorry about that. So the origin creates an initial announcement stating it has a path to destination D, and then it sends the announcements to all its neighbors. So other nodes that receive the announcement pass it on to their neighbors, possibly modifying it. So in the RIP protocol, for example, once this node sends the announcement that it has a route with distance 0, this node will modify it and say, okay, I have a route with distance 1, and then it will send it to its neighbor, and this node will say, okay, I now have a route with distance 2. And when nodes receive multiple announcements, they choose a best one. So here, node 2 may receive announcement from this node as well as from this node, so it's going to have to pick one. And different protocols have different preferences and different orderings for what is considered best. But once it has picked one, then that essentially forms the routing tree. And that's the control plane routing tree that we want to model. And eventually, hopefully, the system converges to a stable solution where no matter how many more messages are exchanged, all nodes are happy with the choices they have made. And this was the essential point made by Griffin and Sobrino. In fact, they identified it as something called the stable paths problem. So here is the imperative stateful program, which is modeling what a control plane protocol is doing, a typical control plane protocol. And what they said is, you can think of it as really a logic model where each node is making, is considering the choices from its neighbors, and then it's picking the best one among them. And then each node is locally stable. So this is a very nice model, which was already well known in the networking community, but all the prior work was done for reasoning about protocol and network convergence of the protocols. Because again, you can imagine when these distributed routing protocols are working on a distributed system, there's fault tolerance to consider. There are other things to consider. People are very concerned about convergence properties. So there was a lot of work done in essentially modeling this as a stable paths problem and showing that many of the protocols that are used in practice are indeed stable. What we did was we applied it for verifying network configurations of protocols in order to do control plane verification. So the main insight that we had was that network protocols are indeed designed to generate stable paths. The routers exchange messages to make the best choice, which in a good protocol, in a good system, which lead to a stable state. So our idea was, let's capture the network control plane behavior in terms of logical constraints, such that the satisfying solutions to those constraints are stable paths in the network. And this was, in some sense, like an analogy to program verification, because in program, often we use, in the SMT-based approach, we use satisfying solutions which represent a path in the program graph on which we check a certain property. In networks too, what we wanted was to come up with a set of constraints such that the satisfying solution represents
why when you're taking a break
in the network graph. But recall that program graphs are often well structured, but in networks, we would have arbitrary graphs due to the network topology. And so a single solution may correspond to many paths. And what we will target is a stable routing tree. So those were our insights. And then the key choices that we made in our model was that we decided to model routing graphs, not paths at a time, which is what many of the previous control plane verifiers had done. And yes, and this is helpful because there are too many paths, but all paths share the same graph. So ours is much more a symbolic graph-based approach. One distinction from the data plane is that the data plane reasoning is done per packet because there is no interference between packets along different paths. So it's okay for you to do path-based reasoning. But in the control plane, routing messages along different paths interact with each other, because the router has to choose the best path among the ones it's available that are available to them. So modeling this interaction can be quite expensive. The second choice that we made was that we decided to not compute states due to exchange of routing messages. Again, this was something that some of the previous control plane verifiers had done. They modeled how the routers are exchanging messages with each other and then created a model checking problem out of it. Instead, we performed search only on the final stable states. And this was due to a familiar lesson that I had from seeing that symbolic model checking often does not scale as well as bounded model checking. In bounded model checking, you simply unroll the whole system up to a certain bound. And because in networks, it's going to be finite anyway, it's akin to doing bounded model checking if you only look for formulas that capture the whole stable state. So now we can solve a search problem over the state space and use modern SAT and SMT solvers. Often, in my experience with hardware and software, this often scales better than computing sets of states iteratively, which is what you would do if you use a standard either explicit or symbolic model checking approach. So these two were some key design decisions that we made right up front. And so our approach was that we created a model called a stable routing paths model, or an SRP model. I'll refer to it a lot during the rest of this talk. You can think of it as a very general logical control plane model. It's framed in terms of local route processing constraints at each router node, just like Sobrino and Griffin had postulated. And then we applied translation to SMT-based logic for verification. And of course, as with any SMT-based verifier, we had to heavily optimize it to make the resulting tool practical. But let me give you a little bit more insight about what this formal model looks like. So formally, an SRP model has these 5 main components. There's the topology, which is the graph with the vertices, which are the routers, and the edges, which are the links between some of them. And there's a special node, which is the destination. We will model the routing announcements in terms of what we call attributes. And these are just any attribute you can pick. It depends on the protocol. And the bottom here indicates absence of a route. So that just means there's no route available. There's a preference relation because we are going to choose the best routing announcements. So it's simply a subset of A cross A. And there's a transfer function, which on an edge, one can modify the announcement that one gets from the neighbor and map it to some other attribute, including dropping it. So that's why it maps to A with the bottom in there. And there's an initial value, that's the initial route announcement, which is provided at the destination node. So I want to point out that the graph topology is, just whatever the topology happens to be. The attributes, the preference relation, the transfer function, and the initial value are often determined by the protocol. And the transfer functions, what happens when you update the announcements from one route, going from one router to another, and the initial values are often what are set by configurations. So really, this is in the spirit of the stable paths problem. It's a logic-based SRP model that we can then create for given protocols and given configurations. And what we will work with, as I mentioned, are the solutions to these formulas. And you can think of the SRP solution as a labeling, which is based on the announcements available from the neighbors, but it essentially maps each vertex to an attribute. And the attribute will tell which one it has chosen. And the SRP solution is locally stable because we want to work only with stable paths. And each SRP solution also corresponds to a forwarding relation, which once you have that, then you can then apply the ACL rules and all to get the data forwarding from it. And
are all these stable things, can they arise during the control plane thing or?
Right. So actually, what we model in our formulas are the actual control plane behavior. So if the formula has no solution, then it is even possible that there's no stable solution, or it may have multiple stable solutions. And that's the point, that we will be checking all possible stable solutions.
Sorry, my question was, but all those that you check can arise in the execution of the actual system. I mean, it's not an over approximation of the stable things.
Correct.
Okay.
But what I want to point out is we are only modeling the stable final states. We are not modeling the transient states
Thanks. Yeah.
before it gets to the stable state. We are only modeling the stable states.
So Aarti, maybe the model is not very clear to me. So you have this graph and you have you have these attributes that are going to be associated with what? With edges?
The attributes are simply, you can think of these as data fields of the routing announcements. And the solution will associate them with a vertex, with each node.
Okay, so with a vertex, I need to associate one attribute.
Well, yeah, some attribute. It can be a tuple, it can be anything. It's a very generic data thing.
Okay, and this initial value, how do I read that? What is that?
The initial value is like the initial routing announcement that I had shown for the destination, which announced I have
at D. Okay.
At D only, yes.
Okay. And there is this transfer function which tells you how on one edge.
When an announcement is sent from one router to another along an edge, it can be modified from the source to the sink.
Okay, so I get some input attribute on E, on sub edge E, and based on that, I update my nodes.
Well,
attribute.
That's the choice available, and then I will pick the best out of that to assign to the sink.
Okay, to the current source, to the current node.
Exactly.
I see.
I'll show you some examples of it in a second.
Okay, so just one last question. So where does the preference come in?
The preference comes in deciding which one I'm going to choose, because remember, there's going to be transfers along every neighbor. Okay, so what will I assign to a node? I will assign to a node according to the preference among the different neighbors.
Okay. So one other question. So are you going to define what exactly locally stable formally means?
Locally stable means that even if you continue to exchange messages, your label for what you decided your node will pick will not change.
Okay, which means it's like something like a fixed point?
Yes, exactly.
Yeah?
Exactly.
Okay.
It is indeed a fixed point.
So why is it locally stable then?
Because there may be some, because each node is only looking at its local neighbors. If there are any dependencies on a global thing, which is very far away, then it may or may not be accounted for properly. And there are certain restrictions under which you can say actually there are restrictions if the transfer function is monotonic, strictly monotonic, then it's also globally stable.
Okay.
But if it's monotonic, then stability is guaranteed.
Okay, so globally stable means that your edges might be paths, is it? I mean, maybe I misunderstood that.
Yeah, we can, this is getting into details which are not quite important. So maybe we can take them offline.
Sure.
Yeah, but again, there's a very rich literature on routing algebras and properties of these transfer functions, which ensure stability locally or which ensure global stability and so on. But my point was we are simply utilizing that work in order to create, logical constraints that we are going to use in our SMT solver.
Okay.
Can I move on?
Yeah, please. Yeah.
Okay. So many, and what we did in the Minesweeper paper was we showed that we can create SRP models for almost all popular protocols, RIP, OSPF, BGP, both BGP, which is external BGP, and internal BGP, static routing, and so on. And what is nice is that Minesweeper handles all of them as these logic-based SRPs. So the uniform model also allows us to handle fancy features like route distribution and so on. And so Minesweeper was really very general. So here's actually an example of the RIP protocol that I had initially demonstrated. The set of attributes here, simply a subset of natural numbers from 0 to 15. That's because RIP, if the distance becomes greater than 15, it just drops the route. So the set of attributes here is just the set of natural numbers from 0 to 15. The preference relation is simply the less than over these numbers. And the transfer function is if A is 15, then if the source attribute is 15, then transfer along the edge will simply drop it because it caps it at 15. Otherwise, it will add 1 to the distance. So you can see how it's really very simple to model the RIP protocol, which actually is based on distributed Bellman-Ford algorithm using this SRP model. And I won't go into the details of what the SRPs look like for all the other things, but you can check the paper or ask me later at the end. So once we have the SRP model, the main approach that we use is to do an SMT encoding for verification. So when we want to check a property P, whether it holds in the network, in the control plane, so the network encoding of an SRP, think of it as N, that's just one big giant formula N, and we will negate the property as we usually do in bounded model checking, and it with that. And now if the formula is satisfiable, then we have found a stable path which violates the property. So this is very similar to program verification, where we negate the property and look for a path that shows the property violation. But if the formula is unsatisfiable, then what this shows is that the property holds for all possible stable paths, which means for all possible data planes that are captured by the configurations and the protocol settings and so on. So really, we are not checking all possible data planes explicitly at all, or one by one. We wouldn't want to. And that's what I mean by a fully symbolic approach. We have, in some sense, captured the effect of all possible data planes that emerge in terms of this formula N.
So
yeah.
A data plane, by data plane, you just mean a fixed point of this network N.
Well, yes, it's a fixed point of this network. Well, we are actually not computing a fixed point at all.
Okay, a stable solution to this.
Yes, we've just characterized the fixed point as a stable solution.
Okay.
Exactly. And so an example of a reachability property, let's say if we have this network and there are some routers here, and we want to check whether router R1 can reach the host H1 over here, we can basically create predicates where we will say that R3 can reach H1 if R3 forwards to H1. And this forwards is the part which in Minesweeper actually can also take into account the data plane, ACL rules, and so on. That's what I meant by we can actually quite easily add that to control plane reachability, because this is control plane reachability and this is data plane forwarding. And as in any logic-based approach, it's quite easy to just create more predicates and combine logically to say what properties we want to check. So here, this would simply be a property can reach R1, and we would negate it and then conjoin it with our formula for the whole control plane behavior and give it off to an SMT solver. So let me tell you a little bit more about how we actually encode it as a transfer function. So you can think of the attributes as if they are states. And the transfer function encodes how the state is updated along a link. Each node has a state. And if we look more carefully along an edge, if this node has a label R3, then Y4 is the label, how that route announcement is changed after using export policy, because each link has an export policy and an import policy, which is captured in the configurations. So we create two different variables for it. One is capturing the export and the other one is capturing based on the import of R2, and then we can essentially model how the attribute gets transferred and gets presented to R2 from R3. And then, of course, R2 will also, so this is just the transfer function part. Then there will also be the logic, which at R2 will pick the best one based on the preference relation. So we will model that also using logic constraints. But again, our attributes, the kind of attributes that we needed for practical examples was, basically just 32-bit numbers in many cases. And here we use the well-known SMT theory of bit vectors and linear integer arithmetic in some cases. So it was quite easy to think of what the protocols and the configurations were manipulating. And by encoding these, we were able to also handle many design features. And these are, I'm not even a networking expert, so I just know that this table was created by Ryan. There are local preferences, there are communities, there are meds, and then there's aggregation, route reflectors, and so on. All of these things, because we are using a very general logic-based approach, it's quite easy and straightforward to capture it using logic constraints. Of course, the formula gets huge, and so that's another problem which we will face later on how to solve that huge giant formula. But at least
in your tool, are these things automatically generated from,
Yes.
From the actual code?
Yes, from the actual configurations, we use Batfish, as I mentioned, as the front end. So Batfish uses, parses the vendor-specific configuration languages and creates a common intermediate format in terms of logic, actually data log-like logic representation. And from that, we did our own encoding into SMT for all these different features.
So the input to this front end is some kind of a, it's a code of the protocol as well as these data structures that the tables.
The protocol itself is specified in the configurations. In fact, many routers will run multiple protocols. So yeah, basically the input to the tool are actual real network configurations.
Sorry, one more thing.
Yeah.
In the model that you described, the graph is given beforehand, and
Yes.
initially you spoke about faults and networking breaking down. So does that mean you have the whole graph including these faults, or can the graph be dynamic?
Yeah. So fault tolerance is handled as a separate issue. And often, in fact, in Minesweeper, what we did was we created extra auxiliary Boolean variables for each link. And if the link is up, it's, the variable is 1. If it's down, it's 0. And so everything is predicated on whether the link is up or not. So one can easily, again, model it in logic. Of course, it becomes expensive, but yes, one can do it. And we did it in Minesweeper. In fact, I'll show you some of the fault tolerance property that we checked.
Okay, thank you.
Yeah.
So, Aarti, one question about the way you model the network. So maybe, is it, how do you get it's essentially, you need to kind of model a fixed point, right? How do you?
We are modeling only the fixed point solutions. So think of it this way. We are saying that every node, whatever its solution is, must be a fixed point of its neighbor's solutions.
So is that like a constraint system of constraint horn clauses?
Exactly.
Okay.
Well, it's not quite horn clauses. There's a lot of disjunction and all over the place. But yes, it's really just a system of constraints which say a solution is a symbolic variable. It should satisfy these constraints that it's locally stable.
So how do you solve these constraints? Do you use a tool or?
Z3.
Okay, that is this mu Z3 or?
Yeah, no, not even new Z3. In fact, this is just plain old Z3.
Okay, so maybe I'm missing something there. So how would it, don't you need to solve this system of equations?
No. I think I am not modeling the fixed point iterations. I'm just postulating that there is a fixed point solution, and I'm calling it, R2's X4. or Y forward.
Okay, but you'll write down the constraints it satisfies.
Correct.
That means it.
Correct.
Okay,
Correct.
but I still don't know. I mean, I have to solve and find out what this R2 is, right? I mean, how does the solver?
No. I am actually not solving the solution. I'm conjoining it with a property negation.
Okay.
So really what I'm looking for is there any solution that would violate the property?
Okay, fine. Okay, so I think I see it. Yeah. Okay.
Yeah. So I'm not actually solving for all possible stable solutions. That would be hard. Then I would need something like horn clause solving or something. Yeah.
Okay, so just essentially like a kind of arithmetic constraints over.
Exactly.
Okay.
Exactly.
Okay, fine.
And so we've checked properties like reachability, bounded path length, equal path lengths, multipath consistency, black holes, router equivalence, and so on. Actually, I haven't said it here, but some of the limitations of our tool is we do not support convergence or checking convergence or quantitative or probabilistic properties because we are using Z3 and we are modeling only the stable states. And checking multiple destinations is also quite expensive. So our evaluation, we wanted to check, can it find some real bugs? And we had a bunch of 100 or so legacy networks, some with many lines of configuration. And what we found was that there were some typical kind of properties they wanted to check. One of these is reachability after any one failure. So we can actually model a single failure by saying, introduce these extra Boolean variables and allow only one of them to be 0. And then can we check reachability and so on. So that would be a general way of doing verification under failures. But there were other properties we checked, like local equivalence, whether black holes occur only at the network edge. And in many cases, we found violations of the property among these legacy networks. And the checking time for many of these was actually pretty reasonable. This is in milliseconds, the time on the left, and these are just the bar chart for the different networks ranging in size according to the lines of configuration. Some were pretty large, as you can see. And yes, it roughly corresponds to the size, but still pretty well behaved. So this was good, and it was a nice, start to trying to basically promote SMT-based modeling and SMT-based verification by taking a very different approach. Instead of modeling the exchanging of messages, we went after the stable states itself, because that's really what is of a lot of interest to network administrators. Of course, there is still the problem that many administrators are also interested in checking transient states. So Minesweeper is not the right tool for that. But apart from that, there is a problem of scale, because as you can imagine, we are modeling everything in a very rich way with a lot of precision about these different features. So the time, what we found was, depending on the property and depending on the actual network, it was about 500 or so that maximum we could check. But industry data centers have thousands of routers, and these days it's upwards of 10,000 and growing. So other technologies such as simulation like Batfish, they also suffer similar but less severe trends. Certainly SMT-based verification is very sensitive to the formula sizes. And so for large networks, that is a problem. So
Aarti, can I ask a question on the previous part? So I'm wondering whether the protocols followed in these, the different routers, would they be able to get arbitrary fixed points, or would they get like least fixed points maybe? And
so actually, that's a great question. I don't even know whether in practice they get least fixed points or not. I think many protocols are very well behaved that they would get a unique fixed point. But for example, BGP is a protocol that's known to have some meta-stable solutions. And in our tool, because we are considering all possible solutions, we would actually verify both of those. So it could switch back and forth between those two because there's no unique solution, but because our methodology is to capture all possible solutions, therefore we would be checking both of them.
Right. So I guess if you don't find a issue, then I guess that is a valid verification.
Exactly.
But if you do find an issue, then that could be a false positive.
I don't think it would be a false positive. It might be that, no, I don't think in this case we are getting a false positive, because it is actually going to show you a stable solution that violates the given property.
Right, but that stable solution may not be realizable by the protocol running on.
No, I mean, we are, why would you say that it's not realizable? Because there might be some exchange of messages that would result in it.
Right. I mean, for
because
example,
we are modeling what transfers happen from the initial state.
Right. I mean, for example, suppose the protocol always gets the least fixed point, but you come up with some other fixed point, which is a counterexample.
And that's what I meant, that I think what we may be doing is, if there are extra things outside of this, if the network administrators are depending on the arrival times of certain things because it's least fixed. My point is that if the protocol allows both least and greatest fixed points, we will be modeling that. If it allows only least fixed points, that's what we would model.
Okay. Okay, thanks.
Okay, so yes, there is this problem of scale because we've got these large formulas and we are modeling everything very precisely. So abstraction to the rescue. And the first thing we did was we decided to use network abstractions based on symmetry, because many data centers have a lot of symmetry in the topology. So what the goal for us was to compute a small compressed network that would have a similar solution to the big one. And here we used a pair of abstraction functions, f and h. The f function abstracts the network topology and the h function abstracts the route announcements, the attributes that I talked about. So pictorially, you can think of this as
Aarti, I think there is one question in the chat. So from someone from the other.
So that's a good question. So the question is, what would happen if there is no stable solution? Is it possible that such a situation happens? Yes. In this case, we can't distinguish that we would get an unsatisfiable because there is no stable there is no stable solution. So in some sense, our assumption is that there is a stable solution, but there can be multiple ones. We can do other things to check and get a stable solution, but that's not what I'm describing. Okay, so yes, we have a pair of abstraction functions, one which maps the concrete nodes in the SRP, in the concrete SRP to the nodes in the abstract SRP. So that's the topology function F. And then we have the route announcement abstraction function H, which instead of B2 might say, okay, it's going to be B. And then we have some technical restrictions. If the abstractions satisfy certain requirements, then we guarantee that it will compute similar global solutions as its related concrete network. And all of this might be actually familiar to people familiar with abstract interpretation. And really what we are doing is we are trying to say that applying the H function to the concrete node solutions gives you the same solution as applying the abstract solution to the representative of that node in the abstract SRP. So with this, we are able to guarantee soundness. And furthermore, this abstraction preserves properties like reachability, routing loops, hop count, multipath consistency, waypointing, but it doesn't preserve fault tolerance. So then this is what we gave up with this abstraction. And we had a tool called Bonsai for control plane compression. And especially in a data center network where you can see there's often a lot of symmetry in topology and in the roles that are played by these routers, one could get a much smaller network. And here I've color coded it to sort of show you what the representative of the different symmetry groups are. So if we are interested in checking reachability, let's say to this particular destination, then this pod is a special one which we will keep as such, but the other pods can be all abstracted away due to symmetry into this much smaller thing. And we showed that the Bonsai algorithm compresses real networks by a factor of 5 to 7 in the number of nodes and 5 to 100 or so in the number of edges, preserves many path properties, as I mentioned, such as reachability, but not fault tolerance. And we proved it correct for a wide range of routing protocols. And by using Bonsai on top of Minesweeper, we were able to show that for fat tree networks, we were able to go beyond 250 or so for all verifying all pairs reachability. We were able to go up to 500 quite easily. And even for a ring network, we were able to improve the performance of plain Minesweeper. The orange one is showing the performance with Bonsai. And as you can see, it shifts more to the right. So it's able to handle larger networks and with smaller time. Lower is better here because we've got time on the y-axis. So that was a very quick thing, but the next question is, what if there is no topological symmetry? Data centers have it, but not all networks have them. And even in data centers, sometimes different policy for different routers can create anti-symmetries or break the symmetry. So one can't always depend on something like Bonsai. So this led us to considering abstract interpretation. And here what we are going to do is we are going to use abstraction on the route announcements, the attributes that I showed you, in order to combat complexity. And you can view this as really formalizing the theory of abstraction for routing protocols, where we combined abstract interpretation, the well-known work by Cuso and Cuso, with the theory of routing algebras, which again was already well known in the networking community due to the work of Sobrino and also combined with Griffin. So let me just give you a very quick overview. Very similar to the SRP model, we start with a topology in a routing algebra, and the algebra has essentially a set of routes. It has a merge function, which picks the best among different routes. We have a transfer function, which given an edge and a route announcement can possibly modify the announcement. And we have an initial route and we have an invalid route. You can think of infinity as dropping a route. So this was just very standard routing algebra. And here is a very small example that runs simplified BGP protocol. So here we've got 5 routers, R1 and R5. Let's say that R1 is the destination. It will announce a route with local preference. So here the attribute is a tuple of a local preference, the path, which is just the list of routers, and a set of community tags. So that's community. This is part of BGP protocol. So R1 is the destination. It will announce a route with local preference 100, which is the default in BGP, and no path so far, and the community tag, there is none. Now, along this edge, you can see that a community tag C1 is added. So if we simulate this network, what we will see here is that the path will get updated to adding R1. And because of adding the C1, we will now see a community tag 1 instead of 0. The local preference doesn't get updated, so it stays the same. And the same announcement also goes out to R2, so we get the route announcement shown here. In the next step, when this is what the transfer function on this edge looks like. So if there is the community tag C1, then the local preference gets updated to 200. So here at R4, it's going to get an announcement where it has 200 R3, R1, because R3 got added to the path, the community tag stayed 1. And from here, it simply got 100 and R1, R2, R1, and 0. And so actually, because of its preference relation for a higher local preference, that's the lexicographic ordering actually in this BGP, it will pick the path from R3, announcement for R3 instead of R2. And it will then send it to R5. And you can see that the updated routing announcement will look something like this in our simplified setting. So this is what happens with the concrete routing algebra. Our idea was to make this abstract. So now let's imagine that we are going to use abstract routing messages where the only thing that we track is a reachability marker R and a community tag, which is either 0, 1, or star for each community tag. So the same example, now we will start with an abstract announcement, which has simply R because it's reachable at the destination already, and the community tag is 0. Then when we go here, because tag got added C1, it will become 1. Here it will stay 0, it will stay reachable. And at this point is where we see the difference. Now it is getting announcements from 2 different places. And because it doesn't know which one is getting picked, it's going to abstract it with a star. So it could be either 0 or it could be 1. And this is the uncertainty due to the abstraction. It's very typical. It's kind of like a merge point in a program where you will merge the 1 and the 0 and make it a star. And then you will propagate it to R star. So the point that I want to show you is that we don't have to necessarily model all the concrete fields of the concrete announcements. We can often work with very simple abstractions of the messages. And that's what we did. We formalized this in terms of abstract routing algebras. We call these A#. And then depending on the different properties of the merges and the monotonicity of the transfer functions and so on, we were able to prove soundness theorems that for a fixed asynchronous schedule, an execution of abstract algebra A# is sound with respect to an execution of concrete algebra A. Here, actually, we are not modeling stable states. We are actually modeling the transient states also. And there's another theorem which says if A# is uniquely converging, and this is due to work again by Sobrino and Griffin, then for any asynchronous schedule, an execution of the abstract algebra is sound with respect to the concrete algebra. And this is formalized in our Popple paper. The thing I want to point out is that there are certain key benefits to abstraction. It can often give precise answers. In our experiments, we got precise answers on 95% of real networks. It certainly improves performance because we are tracking much less information. It creates, it has less memory requirements. It's a smaller state space, so there are fewer iterations needed to converge. And it also creates opportunities for sharing, for example, for multiple destinations. I won't have time to get into details, but we can also create new network analysis. Potential hijacking analysis is described in our paper. And we created a tool called Shapeshifter, which performs very fast reachability analysis. For BGP, we decided to keep only this in an abstraction, and rest everything was abstracted away. And there are other features, nice ones, BDD-based representations, message scheduling heuristics, and modeling multiple protocols, and so on. Let me give you the punchline. When we evaluated it on real networks, the abstract simulation finished in less than 40 seconds on each of our 127 networks, and it was 1 to 2 orders of magnitude faster than concrete simulation in Batfish. So here is the CDF of all the networks that we tried, and the speed up over Batfish is shown on the x-axis. So you can see about half of the networks have more than 50x speed up actually. Furthermore, we were able to show that we were able to prove reachability for all destinations for 95% of the network. And for the remaining 5%, we can prove reachability for the majority of destinations. So the accuracy in practice was fairly good. So this was also very encouraging for us. And of course, on synthetic data centers, as you can imagine, the abstraction really helps. We were able to show much more improvement. This is the concrete simulation time, and this is the abstract simulation time, practically negligible here for up to data center sizes of 500 nodes.
So what do you mean by synthetic data center? You mean
synthetic? I mean, these were not,
things?
Yeah, these were created out of a fat tree topology. And, we didn't have access to an actual real data center network. So, but we took a realistic fat tree topology, which is what a lot of, for example, Microsoft networks and other people use them in their data centers. And then we created policies also for them and configurations through a script. That's what I mean by synthetic. So I know that we are out of time, and actually I'm happy to stop here if that helps, or I can try and maybe do 5 or 10 more minutes for each of the 2 things that I was otherwise going to talk about. Deepak, you can let me know.
Yeah, maybe we can do one of them, maybe spend 5 minutes on one of them.
Okay. Okay, so let me just do the one, because this is my personal favorite. It's my most recent work. And here I wanted to get back to the general SMT-based approach that I had showed you in Minesweeper. And for me, the analogy is, what I showed with Shapeshifter with abstract interpretation. It's kind of like static program analysis versus SMT-based program verification. And the general wisdom is that SMT-based program verification offers more precision. So because path-sensitive static program analysis is harder and more expensive, one often does path-insensitive static program analysis. So I wanted to see what would that mean in the context of network control planes that we are trying to model. So this leads to part 3 of an abstraction, and this is work by my PhD student, Divya Raghunathan, who's incidentally a resident of Bangalore, but currently in Princeton. So recall that in Minesweeper, the SMT-based approaches, we have a network, we have a property, we create an SMT encoding of the network behavior, conjoin it with the negation of the property, throw it to an SMT solver, just standard Z3. If it's unsat, then we know that the property holds in all stable paths, or trivially, there is no stable path. If it is sat, then we know that the property is violated in some stable paths, and one can examine that and fix things. So the question I wanted to ask is, what if we created an abstraction of the network? And so our goal here is to improve scalability, and we adopted a 2-part approach. We created a hierarchy of non-deterministic routing choice abstractions. We call these NRC abstractions, where we abstract away the route selection, choosing the best route, because as I will show, choosing the best route is not essential for certain kinds of properties. The other new innovation in this work is that we also used a new symbolic graph-based SMT encoding, and we also specialized it to SMT solvers that have graph theory support. For example, a solver called Monosat, which is also being used by AWS for their data plane verification. So why does the strategy of abstracting away route selection work? Our insight is that verifying certain properties, for example, basic reachability, may not even need to identify the best route available. And modeling route selection is expensive, especially for complex protocols like BGP. And indeed, one main difference between data plane and control plane is that data planes don't have to select routes. They're already given to you. So our question was, can we get closer to the performance of data plane verifiers if we ignore route selection? And of course, it's a setup question, and the answer is yes. So let me show you how we do it. Our key idea is that each router will non-deterministically choose one of the routes received. Any available route, not necessarily the best, may be chosen. So route announcement fields that are involved only in route selection can be safely abstracted away. But any chosen route must be compliant with policy. If there are routes that are being filtered, in the configurations, for example, based on community tags, then we will model those exactly. So we will model the policy exactly, but not the route selection. And now the abstract network model N prime, of course, has many more routes than the real network, but it will include the best routes and other policy compliant routes. It over approximates N, and we have a hierarchy of NRC abstractions based on ignoring different routing fields in practice for different protocols. And now going back to our SMT-based verification, we will use our abstraction network model. And now if we get unsat, then we know that the property holds in all abstract stable paths and hence in all real stable paths. Of course, now if we get an SAT, it could be a false alarm because the property might be violated in some abstract stable path, which is not the best path, which will not get chosen. So in this case, we do get a false alarm. And I will tell you a little bit more. I will skip through the motivating example. I just wanted to show it to you that here in the abstract network, actually, we will be creating 4 solutions instead of a single solution, which is the best solution in the real network. We'll be considering 4 stable solutions. And because A can reach D in all of these, we actually get a successful verification result. We can have false alarms too. I won't talk about it. Again, soundness is there because of the over approximation. And I'll skip through the encoding. Basically, it uses symbolic graphs, which have a Boolean variable per edge. And it also supports reachability predicates. So by using these predicates and a better solver, we were able to essentially get an encoding of the abstract stable routing trees. And the benefits are that we have fewer variables in our formulas now. And also the search becomes more efficient because expensive transfers become irrelevant during the solver search because we don't have to consider transfers from all neighbors to compute the best. Once a symbolic edge variable is assigned true, other neighbors become irrelevant. So that helps, again, the solver a lot. And we have an Acorn prototype verifier where we used both the monosat solver that has graph theory support and the standard Z3 solver. And let me just show you, so in our evaluation, we compared the performance of NRC abstraction. So with and without using the abstraction. And then we also did the relative performance of the graph theory capable SMT solver. So we did it with 2 solvers, monosat and Z3. Z3, we didn't use any special graph theory support in Z3. And I'll skip through most of this, but I'll be happy to talk about if you have questions. This is a typical fat tree network, and the valley-free policy says you shouldn't be going in and out, up and down in a pod. So it should be valley-free within a pod. If you want to reach this destination, it should be going like this. And this can be implemented using community attributes of BGP, which is often what is also used in data centers these days. And this is the punchline that I really wanted to show to you. What we found, we are comparing with and without abstraction. So abs is with the abstraction, no abs is without the abstraction, and we are comparing monosat and Z3. Really, abstract settings verify both properties without false alarms. And my favorite result, which is that abstraction and monosat was able to verify reachability for a fat tree with close to 37,000 routers in 40 minutes. And I was totally floored when Divya showed me this result because, I would never have thought that we would be able to push it so far. And this is definitely beyond what many of the large data center networks have. I will want to say that these are again synthetic benchmarks in the sense, but they are, a real fat tree topology. And even for the valley-free property, we were able to push it to 6,000 nodes. So I won't, and we found that in all of our experiments for both of the solvers, the abstraction performed uniformly better. And there were some differences, and we also checked with non-symmetric data centers. So these are topology zoo networks. These are real world topologies, and we used a real world business relationship policy. And again, we show that the abstraction always works better than the no abstraction. So lower here is better. These are the ones with abstractions. So the mono is, this one is with abstraction, this is without, and this is Z3 with abstraction, and this is Z3 without. As you can see, abstraction again gives us some benefit. And we had another set of benchmarks. We also performed refinement when we got some false alarms, and we were able to handle it using a trade-off between performance and precision. We also compared ACON with other tools, in particular Shapeshifter that I had mentioned, the abstract interpretation-based tool. I mentioned it uses BDD-based simulation. And NV is another tool created by Dave Walker and his other students. It uses MTBDD, multi-terminal BDD-based simulation, and also SMT. Both NV and Shapeshifter run out of memory at about 3,000 nodes. So it was quite interesting to see that the SMT SAT techniques were more scalable than BDD-based methods. Again, as we had seen in hardware before, as we had seen in software programs before, mainly because the BDDs, the memory becomes a critical bottleneck. Whereas the space-time trade-off, SMT, by doing smart, clever things, we were able to actually scale it up to pretty large centers. So let me just go to the I'll skip the modular verification basically, and I'll be happy to chat about it offline. Let me just show you my final slide, which is some of the lessons that I would say I relearned in applying this kind of strategy to network control planes. We built the logic-based model first. We leveraged domain insights to model just the control plane stable behavior, because this enabled direct use of SMT technology for verification. Another lesson that I've often, preached about is not to abstract too early. Our SMT-based model is rich in detail. It captures many features. For example, local preferences, route distribution, which are considered important by network practitioners. Unless we support them in our tool, unless we can apply them to real configurations, people are not going to be interested in our tool. Once you have a logic-based model, then actually you can throw a lot of logic-based machinery using abstractions, using compositional methods, using CGAR, counterexample guided abstraction refinement, or your favorite method. And that's essentially what we've been doing, applying symmetry, applying abstract interpretation, performing failure analysis. This was work done by Dave Walker and his students. I was not involved in it. ACORN is what I talked about, where we use non-deterministic route selection, and modular verification. I'm sorry, I didn't get a chance to talk about it, but there's many future opportunities, many challenges still remain. Failure analysis, as somebody already asked about. Quantitative probabilistic properties, there is existing work on it. I would love to apply maybe some model counting techniques or probabilistic verification. And one of my other favorite things to do is to combine verification with automated synthesis, and perhaps leverage machine learning plus deductive techniques, which are getting very popular. So let me stop here, and I'm happy to take questions. Sorry for going over time. I'll be happy to make the slides available too if people are interested.
Yeah, thanks, Aarti. Thanks for a great talk. If there are any questions, please go ahead and ask.
Hi, Aarti. Thanks for a really good, brilliant talk. This is really interesting. This is Sanjeeva here.
Thanks, Sanjeeva.
Yeah. I noticed that in the protocols, or the set of protocols that you said you were not able to do was IPv6.
Yes.
And is it because showing the existence of stable paths is just very hard there, or is it something else? Is it just that the state space is enormous?
I think this, it was more an implementation choice. We just modeled everything with 32 bits. We didn't. IPv6 required, I think, a 128-bit something. And
right. No, but I was just curious because mobility is a challenge in finding stable paths.
Right.
And I mean, I have some very old work on that, where interestingly, this point which you make in your final slide of lessons relearned is that first look for stability and then do the abstraction. That's something that we also observed. Then you could get more precise abstractions.
Exactly.
And in fact, very small models which were,
That's
you know,
right.
it's not just small model properties, but tiny model properties. That,
Exactly. And that's been my experience in everything, that it's very hard to recover precision when you don't start from it.
Okay.
But if you start from it in the get-go, one can apply a lot of logic-based machinery on top to address scalability. That's, that's essentially what we ended up doing in our FSOFT program verification efforts also. In the end, it was our SAT-based program verifier that did the job much better than predicate abstraction. Actually.
Right. I think even in program verification, Uday Khedkar has been making this point, is that never sacrifice on precision.
Excellent. I can
Right?
quote him as well.
Yeah, I think he, I'm trying to convince him to write a monograph on it. I think he's agreed. So this is something that for years in program verification he's doing. The other thing which I noticed was that you do a Zoom convergence.
Yes.
Which, I mean, I know that Tim Griffin and his group, Sobrino and others have some results about showing that BGP, or variants of BGP, have a very strong convergence property.
Exactly.
Now, I was just curious if, I've been thinking about this for many years, maybe about 4 or 5 years, that actually any of the class of protocols will, by some kind of Higman's lemma argument, be convergent.
Exactly.
Yeah.
Because, practical
May not be
networks
efficient,
are
but
fine.
it'll converge.
Exactly. And in some sense, by saying, yes, transient state properties are also important. But to me, that's a separate class of properties. Because if you assume that it has converged, you want to know how will it behave after that.
Yeah.
And we were able to, I believe we were the first ones to focus on stable states alone in the verification approach that we took.
Yeah, we did a bit in HVC paper 2015 with respect to reachability in mobile networks.
Right.
Again, we did this business of first reach stability, and then you'll be able to verify reachability.
Right.
So I think that's a pretty important lesson which is out there.
Yeah, and in fact, even for the shapeshifter work, which is based on abstract interpretation, we use the results, the latest ones from, I think, 2017 of Griffin, because they actually did, I believe in Cork, they proved certain things about the convergence.
This is with his student Daggett or something, right?
Daggett, exactly.
Okay.
It's the Daggett reference, which basically shows that if you can take a synchronous semantics, you don't have to worry about the asynchronous message ordering.
Exactly.
Yeah. And in fact, our abstract interpretation result is based on the synchronous semantics.
Okay.
And
Yeah,
in
I'm
fact,
just
I didn't get a chance to talk about it, but that's what we're also using in our modular verification, the synchronous semantics of Daggett and all.
Okay. I was also just curious about what the abstraction concretion, the Galois connection looks like. What is the concretion?
The concretion is simply, I can try and go back to, no, it's not letting me go back. So if you recall my example, we had the community tag becoming a star.
Right.
And so the star is the abstract data, and the concrete data would be 0 or 1.
Okay. But what would your concretion take you to the set 0, 1, or would it?
Yes, the concrete would then take you to both sets 0 and 1.
Okay.
And therefore, if you reachability depended on it,
Okay.
for soundness, you would have to say it is not reachable.
Okay. Okay.
And that's how you would get false alarms.
Okay. Great.
Yeah.
Thanks,
and actually
Aarti.
our paper does describe many different abstract, in some sense, domains for the different kind of routing attributes.
Okay. Great.
We have a table of that, yeah, in the POPL paper.
So this is the POPL 2020.
Yes, this is the POPL.
Okay. Okay. Thanks. Thanks, Aarti.
Of course, anytime. I saw a question in the chat, I think.
Yeah,
Can
maybe
this
we can
formal
just
verification?
both.
Sorry?
I think there's one about in Minesweeper and Shapeshifter. Is there a specific logic language in which the network properties are written?
No, actually, we just allowed anybody to use any SMT
Okay.
formula.
Okay. And then I think there's a question from Narayan Kumar. I think he had to leave early, but
Okay.
what are the specific features of the formulas that arose in this problem that are challenging or different from other applications of SMT?
So one of the things that we saw is that, there was a lot of duplication of variables. And if there was not much happening in the transfer, we would simply get, oh, y is equal to x. Or if there's not export policy, we were just getting a lot of simple propagations. So some of the, and our Minesweeper paper describes some of the optimizations that we did. So it's the usual kind of formula simplification ideas, typical in compilers and so on, in order to simplify the formula. But I don't think that that I can say whether the characteristics of the formula were very different from other known things, because as we saw, it's usually the number of neighbors of any router is not that many. So it was mostly just trying to relate those and doing a lexicographic ordering on those and so on. So I think it's not that different from any system of constraints that you can imagine would happen in a recursive formulation like this.
Okay. And there's a question from Bhavana. Can this formal verification method be applied in distributed system networks?
So what do you mean by distributed system networks? Because I talked about, so if it's network, the network will have either distributed control planes. Do you mean data center networks? Do you mean software defined networks? So yes, we can certainly handle data center networks that are typical.
So, Bhavna, if you're there, you could clarify your question. Okay, maybe she's not there. Yeah, sorry, Aarti, go ahead. Yeah.
No worries.
Okay.
Aarti, I had another question. Suppose
Sure.
we didn't look at these policy-rich networks that Griffin and Sobrino have been talking about, but look at policy-poor ones, where you have actually a semi-ring or something sitting underneath. Does that abstraction concretion become much easier?
I'm sure it would.
Yeah. So then you can get more precise abstractions almost always?
I haven't tried it, so I can't say, but I think your intuition is right. We should be able to get fairly, even for these policy rich ones, okay, the 5% false alarms that we got were due to things like regular expressions, which we are currently not modeling.
Okay.
In Shapeshifter. If we added a domain for it, we might be able to handle it.
Okay.
And actually, it's something that we added in Acorn, because in Acorn, using this monosat solver, we can actually handle regular expressions over AS routers.
Okay.
Yeah. So it's more a matter of, I think, implementing it, creating an abstract domain for it. In principle, I don't think there are showstoppers there.
Thanks, sir.
Yeah.
Right.
Sure.
Right. So
Sorry,
thanks a
one
lot.
more
Yeah.
question.
Yeah. Is there another question? Yeah, go ahead.
Sorry.
Yes.
Do you consider bigger networks like global networks where you take into consideration AS routers as you just mentioned, or is it only data center specific networks?
No, actually, I'm sorry, I skipped through that very fast. Let me see if I can go back and show you actually some results in Acorn of not data center networks. So this was a real internet topology. And here we used a policy which implements what are called Gao-Rexford conditions, which says that, so every AS here is given a label, it's a customer or a peer or a provider. And you prefer customers to peers to providers because you have to pay to providers. So one of the common properties that people want to enforce is that don't export routes from peer and providers to other peer and providers. And here is an implementation of it using the community attribute in a BGP protocol. So we actually checked this kind of a policy in many topology zoo benchmarks, which we created. So these unfortunately were not even available because topology zoo is publicly available, but only topologies. So we created the policy for this common Gao-Rexford condition, and we were able to check it. As you can see, the times here are much smaller than data center networks. This is less than a second. And the sizes are also not very large. In fact, these were some of the larger topology zoo benchmarks. Another data set that we created, by the way, if you're interested, we have made all our benchmarks publicly available, the newly created ones as well. These were created from BGP Stream. BGP Stream are, again, they report real vulnerabilities in CIDA, and they maintain a CIDA data set for business relationships. So we created actually slightly larger benchmarks. And again, here there's no symmetry. These are not data centers. These are wide area networks. And we checked again that no transit property. In this case, for reachability, we actually found that there were false alarms in 4 out of the 10 networks. But again, we found that abstract settings are better than concrete settings, and we get speed up both with monosat solver. With Z3, the benefit was not as pronounced. So these are actually examples on AS networks where we just postulated the customer provider peer relationships and checked for a property which is a common business relationship that people enforce. Does that answer your question?
Yeah, thank you. Thank you so much.
Okay, I think it's been a long day, so especially for Aarti. So Aarti,
No
thanks a
worries.
lot.
Yeah, thank you so
It's been
much.
a great talk and a very rich, I think, interesting problem and a rich kind of, space for solutions and applying logical and program analysis techniques. So
Yeah,
very interesting.
It's kept me very busy and happy for the last many years.
Okay, so let's just unmute and give Aarti a hand. Thank you, Aarti.
Thank you so much. I appreciate it. And again, thanks for inviting me, Deepak.
Thanks, Aarti. Yeah,
Bye.
Yeah, please get in touch whenever you
Sure,
would
I will.
like to come across and visit us.
Definitely.
Okay.
Thanks, everyone. Thank you.
Thanks, everyone, for joining. Yeah.
Yeah, bye.
Thank you.